Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be talking about subbasin losses like infiltration methods, specifically the Smith-Parlange and soil moisture accounting methods. All right, what I have on the screen here is a subbasin, and there's multiple subbasins because this has been a full watershed that's been delineated. I only really need one subbasin to describe the two different loss methods, though, Smith, Parling, and soil moisture. So we go over here to the subbasin tab in the components editor. The loss method here, we have a lot of choices from none, deficit and constant, exponential, and so on. The ones we were going to talk about here is the last two, Smith, Parling, and if I'm saying that right, and soil moisture accounting, as well as the gridded soil moisture accounting. All right, so let's start off with the first one, Smith-Parling, and then head over to the loss tab here, and we have a bunch of parameters that we need to fill out. The Smith-Parling loss method should only be used for event simulations and not for long-term simulations. This approach approximates the wetting front with an exponential scaling of saturated conductivity, enabling faster computations with reasonable accuracy. This infiltration method has faster rates at the beginning and then slower rates later in the simulation as the soil becomes more and more saturated. Now let's talk about the parameters for this loss method. In the component editor, we see that they're all required except for this last one, temperature gauge, but we'll do that one as well. All right, the first one is initial content. This is talking about the initial volumetric water content. So at the beginning of the simulation, there's going to be a volume of water divided by the volume of total soil. So this is going to be, I'm going to type in some numbers like 0.3. And then below that is the residual content. This represents the volumetric water content, again, of the soil after all the drainage has ceased. So there will still be a little bit of water in the soil. And I'm just going to use the number from the user's manual as well. Most of these values are user's manual example values, except where I've had to convert from metric into English units. The saturated content, again, is a volumetric water content, and this represents the total volume of water divided by the total volume. And this is assumed to be the total porosity of the soil. All right, next up is the bubbling pressure, and this is in inches. So think of it as head, for instance. This represents the pressure required to initiate the displacement of air by water in the soil's pores during infiltration. This pressure is primarily influenced by soil texture, where finer grained soils like clays will have higher values and require more pressure, whereas more porous soils would have lower bubbling pressures. Let's go ahead and say 8 inches. The next field down is pore size distribution, and this refers to how the total volume of pores is distributed within that soil. For instance, for the same porosity, you could have fewer large pores, and that would result in higher infiltration, or you could have more smaller pores, and that would result in less infiltration. So 0.252 is the example number there. Conductivity here, this is the saturated hydraulic conductivity. They just seem to sort of abbreviate the labels here, but you can hover over and it'll tell you what it is. This is in inches per hour because I'm using US customary units, and you can just type in whatever value it is. The bubbling pressure and the hydraulic conductivity can be determined from laboratory testing, but it can also be looked up and approximated based on the soil type or soil texture, it's sometimes called. The next one up is the percent impervious. We've seen this before in other loss methods in HMS, and this refers to the area of the subbasin that has impervious soil, basically the percent of area that has zero infiltration. And then the last one is the temperature gauge. So the temperature of the water does affect the density and the viscosity slightly. So if there's no value provided, then HMS assumes 75 degrees Fahrenheit and I believe 25 degrees Celsius. But if you want to actually add a temperature gauge data over the duration of the simulation, then you would go ahead and add a time series data. Let's go ahead and do that now. We'll go up to a components menu and then time series data manager. For the data type, we want to select temperature gauges and then new. And then just type in or paste in the name for that gauge with an optional description. Click create. Okay, that's good. Now this is enabled and we have our water temperature time series data set that we can select. If this is selected, we also need to select this beta 0 value. For US customary units, the user's manual has a table to kind of show the range. So for something like sands and high porous materials, it's going to be closer to like negative 405. But if it's for more fine grained soils like clays, that's going to be negative 376. So those are sort of the range of values there. It represents the tension or negative pressure exerted on water within the soil matrix, influencing how tightly water is held to its availability to plants. Those are the parameters required for using the Smith-Parlange loss method in HMS. Next, we're going to transition into the other method. So I'm going to select sub-basin, and then instead of Smith-Parlange, it's called soil moisture accounting. So I'm going to go ahead and select that and then go over to the loss tab. And we see a ton of parameters here, but it's really not as many as you think because they're sort of grouped into three different types. Also worth mentioning is just because we're talking about soil moisture accounting, there's also a gridded soil moisture accounting method here, which we'll talk about at the end of the lesson, but there is significant overlap. So just keep that in mind. All right, so soil moisture accounting, I'll select that one and then I'll select Loss tab. Before diving into the details, the soil moisture accounting loss method is a continuous simulation type method, not really used for a single event. This method should be used with a canopy to extract water and dry out the soil layer between precipitation events. And it should also be used, oftentimes used with a surface method, which will hold water for infiltration. The main idea behind this loss method is that there's three layers that the water moves from: the surface into the soil layers, the first layer, and then below that is a top of the upper groundwater level layer, and then below that is the second or lower groundwater level layer. Infiltration occurs faster when the upper layer there's more water or water content in the upper layer, and the lower layer is drier. And there's slower infiltration or percolation when the upper layer is drier and the lower layer is more saturated. Okay, what I have on the screen here is from the HEC HMS Technical Reference Manual, and I found this because it provided some background and detail about this particular method. The user's manual does talk about it, but it doesn't provide the same level of detail, and it certainly doesn't provide the equations, which I really like to see. And that's what I brought this in for. So we have this first equation, and this represents the potential soil infiltration. It's basically the maximum soil infiltration minus, and then a fraction of the maximum soil infiltration. So they probably could have just written this: maximum soil infiltration equals the quantity 1 minus, and then this quotient here, representing the soil storage values for current and maximum. Now, the actual infiltration rate here is the minimum value between this potential value and the volume of water available for infiltration. This equation refers to the top level of surface into that top level of soil. But remember, there's two other layers in this layer approach towards infiltration. And those equations are down here. So equation 2 is from the soil layer into the top groundwater level layer. And then this third equation down here is from the top groundwater level to the bottom, to the lower groundwater layer. There's some simplification and some more discussion here. I'll leave a link to this page in the description to this video. Let's start filling out the parameters. So we'll say 67% is the initial volumetric water content. That's in the soil layer. And then the same thing, but for the groundwater level 1, we'll say is 50% and 82%. So these three fields are all similar. It's that initial water content by volume. This maximum infiltration value is hydraulic conductivity. We saw this in that equation. I'll just say 2.1 inches per hour. This is the upper bound of the infiltration rate from the surface storage into the soil. The actual infiltration rate also takes into account surface and soil storage. The next field down is our percent impervious. We've seen that before. We'll just leave that at 0%. Next up is soil storage, tension storage, and then I should also say that groundwater 1 storage and groundwater 2 storage, these four fields are all related because they're all related to storage with units of inches. So keep in mind that depth of inches is multiplied by the entire area of the subbasin or the entire area of the grid when we get to the gridded method to represent a volume of water. So for soil storage, we'll go ahead and say 9.4 inches. For groundwater storage, I'll say 10.5 inches. For groundwater 2 storage, how about 14.5 inches? These storages represent the total storage available in each layer and in inches. The tension storage, I'll just type a number in here. How about 8.3 inches? This is the amount of water storage in the soil layer that does not drain under the effect of gravity. So the percolation can only take place from the soil layer into the upper groundwater level layer when the current soil storage exceeds the tension storage. The next field here is the soil percolation in inches per hour. And then we also have fields for groundwater 1 percolation and groundwater 2 percolation. So these three fields all represent the maximum percolation rate in these three layers. So I'm going to just type in some numbers here, 0.17, 0.048, 0.035. The actual percolation rate is a linear function between the two layers that the percolation is occurring between. The last two fields here is refer to groundwater 1 coefficient and groundwater 2 coefficient. I'll just type in some numbers. The groundwater 2 coefficient is most always going to be a larger number. This refers to the time lag for transforming water in storage to become lateral outflow, which is available to become base flow. So these are the parameters for the soil moisture accounting loss method. These are just some typical values to get you started. We also have the gridded soil moisture accounting method, which is essentially implements the soil moisture accounting method on a grid cell by grid cell basis using the grid data manager in the components menu. So what that looks like is I'll go back to Subbasin. We'll switch from soil moisture accounting to gridded soil moisture accounting. Now let's select the loss tab. And here are all the parameters, but they're pretty much the same as the parameters we just saw, except most of them operate on a grid, except for these first few that I can already type in without any grid data. So I'm going to go ahead and do that. This initial soil here represents the initial soil storage, and it's a required field. So I'll type in, say, 67%. Initial groundwater, we'll say is 50%. Groundwater 2 will be 82%. Now we need to provide some grids to our HMS model. And the first one will be for max infiltration. I also want to include the soil percolation grid, the groundwater 1 percolation grid, and the groundwater 2 percolation grid. So we're going to go up to our components menu, click on Grid Data Manager. Once I have percolation rate grids selected, I'll click New. And then I'll just paste in a name, and then that'll be for the max infiltration. I've got a few more I want to add while I'm here. So let me just paste in, that'll be for the soil. I need one for the groundwater 1 layer, and then I need one for the groundwater 2 layer, and then we're good. All right, I'm going to close that. I've collapsed the Watershed Explorer, but we now have grid data directory, and inside that, percolation rate grids. So these are the grids that we just created. When we select a grid, we also need to define the data. So right down here in the components editor, this is where we specify the data source. And then based on that data source, we also need to provide any other required data. So in the case of a DSS file, we need to provide the file name and the file path. All right, so now that we've done that, let's go back to our Subbasin, the loss tab. And for max infiltration, we can select our max infiltration grid, the soil percolation grid, which would be right here. You can name it whatever you want. This will be groundwater 1, and then here is groundwater 2. The next batch of grids that we need to define are for storage. So again, we talked about this in the non-gridded version, but now we have to create a grid data for it, not just a single value. So we have the soil storage grid, we have the tension storage grid, and then a groundwater 1 storage grid and groundwater 2 storage grid. To get these grids loaded in, we'll go Components, Grid Data Manager again. But instead of precipitation, or we had percolation before, now we want to use storage capacity grids. So go ahead and select that, then click New. Here's the name. I'm going to paste that in. And then as before, I'm going to add a few more while I'm here. This is for the groundwater 2, the lower groundwater level. Now we can come back to our components editor and make those selections. So this is for storage. This is going to be for tension. This is groundwater 1 storage. I'm using this 45 as sort of a suffix to represent this particular subbasin. And then this is going to be groundwater 2. We have just 2 more to go. This is the grids for the coefficient. So right now I can't click it. It says none. We'll go ahead and go components. and then Grid Data Manager again. We're going to select storage coefficient grids. So we have our percolation, and then we added our storage capacity. And now we have storage coefficient grids right here. Click New, groundwater 1 level, and New, one more, and then boom, and create. Okay. So let's double check that that worked, and it did. So there's groundwater 1 level and groundwater 2. So that is it for our different methods. We use the Smith-Parlange method of infiltration loss, as well as the soil moisture accounting method, both non-gridded and gridded options in this tutorial, to demonstrate just a few more options on how losses work in subbasins in HEC HMS.